Here we're going to demonstrate two samples of electrical network using SNAP. First, let us open up the circuit editor. Here on the right hand side, we got a list of devices that we can put together a circuit. Example, I will highlight the inductor. Here on the desktop, I click the left button and then the right key to rotate it. If I hit the delete key, that will disappear. Now to drop an capacitor, we do the same thing, but this time we're going to rotate it, like for the resistor. To position it, we got to click the select bottom menu, and then we can position the component. I'm going to drop an input signal source. I will position it so that same thing with position the output. Click the line to start wiring up the diagram. Double click the component to fill up the parameter value, but we got to hit to make sure we got in the select menu. Then we will assign value to it, nominal value. I'll put an equal sign. Show parameter, don't show the name anymore. Then we can save this in a suitable folder. In my case, it is under the snap folder of the EE 453. Then supply the name. LCD RLC underscore EQ. And I'll just open what I have done before. And on top of that, notice I provided the text that you can fill this up, and then when you click OK, then you can position when you select that. That's what I did here to create those two lines. This is similar to what just illustrated earlier, except now I label them L1, L2, C2, R1. A different configuration from the one. Now this has already been saved. So to do the analysis, I click the analysis. Maybe I should show the node. There are nodes now, 1, 2, 3, 4, 5. To produce the needed transfer function according to the derivation provided in the page, I call it quotient, using ABC and by hand calculation, the output at voltage 4 divided by voltage in is s squared plus 1 over 3s cubed, 2s squared plus 2s plus 1. Well, this SNAP symbolic program is capable of generating that. Let me activate the SNAP. Click the network function, voltage gain right there. The numerator is L2 times C2 times R1 S squared plus R1. Denominator is in the ascending power R1 plus S times L3 plus L1 and so on. This is the coefficient of S squared. This is the coefficient S cubed. It also provides the so-called multiple dipole zeros and the time response equation as well as for the pulse. Now here, if we click the second menu, we will get the frequency response. If we click the third one, we get the time response. We can also go beyond that. If we click the Then we click the grid to display the grid so you can see clearly how they are progressing. Click the setup. We will step the parameter, so I click the step. Select a parameter. How about the first L1 linearly from say 0.2 to 2 Henry, 10 of them. That's it. While the stepping is still valid, we can click the time response. Step. The second parameter, L1, from 0.2 likewise. Let us step the third parameter, which is L2. Likewise from 0.2 to 2, 10 steps. And we can likewise see the time step response. Next, let me illustrate another sample. I will close this and open up the one given in the book by Kendall Sue, page 235, the design of multiple feedback bandpass filter. Example 1-4. The filter given in the book is configured like this, where the resistor R1, R2, C1, C2 are normalized. R1, C1 is equal to C2 equal to F farad. R1 is 1/4 ohm and R2 is 4 ohm. The normalized center frequency is 1 radian per second. Well, let us scale the impedance so it will be 1,000 times. So 1/4 ohm becomes 250 ohm and 4 ohm becomes 4K ohm. Let us also scale the 1 radian per second center frequency to a kilohertz. Therefore, the scaling frequency is 2 pi 1 kilo divided by 1. That is 6,280. Then using the frequency and impedance scaling, the resistor is not affected by frequency scaling. So here is the transfer function, precisely the formula given in the book by Kendall Sue on page 234. This is the bandpass frequency response, where the center frequency as we specified it at 1 kilohertz, and this is the corresponding time step response. Likewise, we can step the parameter. Let's try the R1, let us say starting from 100 to 500. Let us